Okay, welcome everybody. It's a pleasure to have you today. It's a pleasure to have today with us Professor Norbert from the University of Bonn. Actually, he's the director of the Argelander Institute for Astrophysics there. And he is an expert, a world-recognized expert in stellar structure and evolution, nucleosynthesis, and particularly in the realm of massive stars, supernovae, and related processes that happened in the interior of those stars. And to make a brief presentation of his career, he started physics and PhD studies in Göttingen, made a PhD with Professor Fricke. And then after a few years of postdoc travel, tourism, as we all do at some point, he was awarded a professorship at Utrecht University, and from there he moved to his present position in Bonn. However, well, as interesting all these personal details are, actually these are not the reason why we are so pleased to have him here. It's just because of his really deep knowledge of the structure of and evolution of massive stars. And Norbert, thank you very much for finding time to come to visit us.
Thank you very much, Artemio, for your introduction and also for inviting me to be here today. It's a pleasure to be in this important institute, and I know that many of you have deadlines, so thank all of you for being here. I want to talk today about main sequence stars. Actually, main sequence stars is one of my favorite topics. And whenever I tell that an astronomer, then I get the comment that main sequence stars, what's interesting about them? Now here is a big solar physics group, so at least there's one main sequence star which many of you like, and it will also feature in my talk today a little bit. But I hope I can explain to you that main sequence stars are not well understood, at least if we go to massive stars. And this has to do with the stellar Eddington limit. So I guess all of you know what the stellar Eddington limit is about. What I will try to convey today is that while stars evolve on nuclear timescales, we can watch many of them change in front of our eyes. And to mention a few examples, there's spectral variability in many stars. For example, in our sun, there's a granulation of the sun which leads to that. There's pulsations. This is a Cepheid light curve here. Some stars even have things like eruptions, which we're not quite sure we understand. Now, I will argue that all this phenomena may have a common origin and is related to the problems which some stars have to shine, which means the problems to release the radiation from the interior to space. Now that's of course what the Eddington limit is about. So just briefly, if we consider the photon momentum acceleration at any point in the star near the surface, for example, and this is just exactly balancing gravity, local gravity, then this is what defines the condition of the Eddington limit. And we can transform this into the equation which you probably all know. And now we use the Eddington factor gamma as the luminosity of a star divided by its Eddington luminosity. And of course the big question is what happens if the Eddington limit is exceeded. So This question has mostly been raised for massive stars, and the reason for that is that, well, the main sequence stars obey a so-called mass-luminosity relation. Again, you're surely familiar with that. Mass-luminosity relation is observationally well tested. It's one of the most fundamental predictions of stellar structure theory. And now it has the feature that for masses becoming very large, the exponent here, alpha, goes to 1. So for masses near our sun, we have a very steep relation. Maybe alpha is of the order of 5. But if we go to very massive stars, this turns towards 1. And so usually you don't see that on plots, but if we look at observed stars in the mass luminosity plane, you see that the main sequence stars really obey such a relation very closely. The turnover you don't quite see, it comes up here. And now just very briefly, the Eddington limit for electron scattering. That's the Eddington limit in the form where it's mostly discussed. So see in the Eddington limit, the opacity coefficient enters here, which measures what fraction of the photon momentum is actually absorbed and leading to outwards acceleration. Now, many stars have a simple opacity law where just electron scattering is important. It just depends on the hydrogen fraction, is otherwise constant. So if we assume solar composition, then we get a very simple relation that the Eddington luminosity is simply proportional to the mass of the star. And if we then plug in numbers, then we see that our sun would be very, very far away from the Eddington limit. And 10 solar masses, we are at 3%. 100 solar masses, we are at 30% of the Eddington limit in this approximation. So still far away. Now it turns out that you need to go to 10 to the 5 solar masses to actually hit the Eddington limit when you only take electron scattering opacity into account. So how does that look like? So here we have again luminosity and mass of stars, of main sequence stars. So the 0H main sequence is located here. Mass luminosity relation is steep and then it flattens out. And this is the relation for the Eddington limit with electron scattering opacity. And so you see the slopes become the same nearly here. And that's why these lines only cross very far away at 10 to the 5 solar luminosities. So this could make you think that the Eddington limit really doesn't play much of a role in stars, because 10 to the 5 solar masses we're not interested in. Not very much. Sometimes we are, but not very much. Now, the point is we need to look at the complete opacity. And besides electron scattering, there is free-free, absorption, bound-free, bound-bound, and so on. And so I've shown here examples of opacity as function of temperature for different parameters R, which are defined as temperature divided by density cubed. Sorry, it's a bit small, but the main feature you can see anyway. So this is opacity, this is temperature. And in the massive stars, the peak produced by iron is most important. And so this is the electron scattering level here, 0.34 roughly. You see that the iron peak can be 2 or 3 times as high as the electron scattering opacity itself. If we go to low mass stars, we get even higher opacity coefficients that mostly relate to hydrogen recombination. You see, again, very small, but the big peak here is due to hydrogen, and this is a logarithmic scale which goes up to 10 to the 5. So the hydrogen opacity can be even up to 10 to the 5 times that of electron scattering. Now, of course, what we can then do is we can go to our mass luminosity plane and see what happens if we include a higher opacity here for iron, a factor of 3. So this brings down the Eddington limit by this factor of 3. And now you see suddenly the lines cross here at 100 solar masses. Actually, this is the zero age main sequence. If we look at terminal age main sequence models, still main sequence, then these models are a little bit more luminous, and we see the crossing point is at 30 solar masses. So from this very simple consideration, now we would expect stars above 30 solar masses to be affected maybe by the Eddington limit. We can do the same thing for the hydrogen luminosity. There we had a factor of up to 10 to the 5. Naja, I just put a factor of 10 to the 3 here, then we come down to 5 solar masses or so. But in the sun, really, the opacity is even much higher. And so suddenly, even the sun could be very close to the Eddington limit. And I will argue, actually, that is the case. Okay, so let's first talk about massive stars. So this is a grid of evolutionary models, black without rotation, red and blue with rotation, and the Hertzsprung-Russell diagram. And ignore all the funny tracks, it's not so important, it just shows you which luminosity scale we are. Now we computed models of up to 500 solar masses to really be sure we see the Eddington limit in our models. And so what we did is we use a different diagram to work with in the end. So this is not the Hertzsprung-Russell diagram, this is so-called spectroscopic Hertzsprung-Russell diagram. So what is plotted here is not the luminosity, but the effective temperature to the 4th power divided by the surface gravity. Now this may appear strange to you, but it has the advantage, first of all, that these two quantities can be measured spectroscopically without knowing the distance of stars, so it's quite convenient. And the second thing, which is most important for this talk, is that this quantity is directly proportional to the Eddington factor. It's actually proportional to the ratio of mass to luminosity. And so you see the logarithm of the Eddington factor plotted here. And so the Eddington limit is where the Eddington factor is 1, the logarithm is 0. Now that's true for solar composition. If we would have helium-rich surfaces, we have less electron scattering opacity, then the Eddington limit can be a little bit higher up. So I'm just explaining that because it comes up later. So you see that all the models here seem to behave relatively well. They remain below the electron scattering Eddington limit. And that's good because otherwise these models should not exist. They shouldn't be stable. So the first thing we looked at is we checked what the Eddington factor using the full opacity now is at the surface of these models. And what you see is the result here. It's color-coded, so it's so the colors are such that red means the Eddington factor at the surface is 1. And you don't need to worry about the colors otherwise too much because red occurs only here. That means essentially all these models here have Eddington factors at the surface which are below 1, even if we take the full stellar opacity into account. Actually, these models here are kind of peculiar. They are very helium-rich and they correspond to Wolf-Rayet stars, and I don't want to discuss them here, but if I go back, you would see that these belong to the very most massive stars, 500 solar masses, very helium-rich, so maybe they don't even exist in nature. The message from this picture is, at the surface, even taking the full Eddington factor into account, the massive star models never reach the Eddington limit. And this has to do with the opacity behavior, which we can see here. So essentially what these different curves are is solutions through the stellar envelope with decreasing density. So if the density becomes lower and lower, you see the opacity becomes lower and lower. Now the lowest density occurs at the surface of the star, and it turns out that there the opacities are small enough such that we don't have any problems with the Eddington limit. So that's just what I said. Now, in the deep interior, the stars should also not have any problem with the Eddington limit, because what one can show is that when in the interior the Eddington factor approaches 1, then actually convection occurs. And of course, if convection transports the energy, then we don't get any radiation pressure from this. So we actually only need to worry about the part of the energy which is transported by radiation. So we need to look at the radiative luminosity. However, it turns out that there are layers beneath the surface where the density is so low that convection is actually inefficient. What does that mean? So convection wants to transport energy. There's moving blobs which are hotter than the surrounding. But then because the density is already so low, what happens is that the energy of the blob is radiated to the surrounding faster than the blob can rise. So that means convection is inefficient and cannot really help to transport much energy. However, the density is still high enough for having high opacity. And so as a consequence, the massive stars turn out to actually reach and even exceed the Eddington limit in these subsurface layers. So what you see here is the same plot as previously for our model grid. And color-coded, you see now the maximum Eddington factor, which only takes into account the radiatively transported part of the energy flow inside the star, so beneath the surface. And there you see that essentially everything which is red or blue exceeds the Eddington limit. So all these guys do exceed the Eddington limit. So do approach it or exceed it. So blue means the Eddington factor is actually larger than 1. Now, of course, what that would imply is, what we would first expect is that it should push off the layers above. But these models have a trick. They introduce a density inversion such that the gas pressure gradient is directed inwards, stabilizing. And so they can have actually an Eddington factor somewhat above 1 and still be hydrostatically stable. Now, you may think that is a funny structure. I come back to that. I think it's probably a real phenomenon. So what happens, however, in these models is that they inflate. Maybe I should have pointed that out earlier. So all these models which you see here, so you see evolutionary tracks here of 50, 100 solar masses, they're all still burning hydrogen in their cores, but their surfaces reach temperatures of below 10,000 Kelvin or so. And so this is very, very extended core hydrogen burning stars. And so we call this phenomenon inflation. And this is a typical density structure of one of our inflated models. You see the parameters here. If the Eddington limit would not exist, then these stars would end here. So this particular star would have a radius of 30 solar radii, perhaps. But inflation leads to this low density extension of the star. It actually makes the star a factor of 3 or 4 times bigger in this case. And how does it come about? Well, the star evolved. The opacity in the envelope increased because the star became cooler. So the layers below the surface did exceed the Eddington limit, and as a consequence, they pushed the layers above further out. This has the effect of decreasing the density, and that's why the star then could actually avoid becoming unstable, because the opacity was limited in that way. So this is a very funny structure. We have inflated main sequence stars. There's also a density inversion occurring here, as I told you. In these layers, the Eddington factor is larger than 1. And so we can wonder has this anything to do with the stars we know, with reality? And so far, we don't know. But it's a very basic phenomenon. The Eddington limit it's not possible to avoid to see the Eddington limit in these models. Now, one of the limitations is our models are 1D, spherically symmetric. So very recently, actually last week, there was a paper on AstroPH by Young et al. They did 3D simulations of such inflated structures. And the result is shown here, or one of the models. They did 3 models. So this is a radius scale here, 30 solar radii, 60, 90. And color-coded is density. High density is red, low density is blue. So you see that also this is not exactly the initial model, but a model very close to when the simulation started. You see that there's high density here, there's high density here, in the middle there is the inflation zone. So it's exactly the same structure as I explained you before. And what they do is they turn on time and they treat radiation transport and convection in a very nice way. And so this is one of the models at very late time. And there's 2 things which you can see from this. One is that the stellar radius is still pretty much as it was before. So this inflated structure, in a sense, is still there. The star did not collapse. The question was whether perhaps the porous density structure here would allow photons to escape without much interaction, and then the envelope could collapse to an uninflated structure. That's not observed. And the other thing is that they even find in the time average structure that the density inversion is also persistent. So you see here blobs which have pretty high density. So even in these 3D models, we can say that a density inversion is also still there. So 1D is not the key problem here. The 3D models show essentially the same thing. So when the stars hit the Eddington limit, we see inflation. So here you see the degree of inflation in our models, which is measured in delta R over R core. R core is the radius of our models when the Eddington limit doesn't play a role. And so you see that in this region we have extensions of 50% or 100%. And below this line, the models are a factor of 2 or 3 larger than they would be otherwise. Now this is a plot which I just want to show. So you see that really the Eddington limit is the culprit. It shows here the maximum Eddington factor in our models, and here the strength of inflation. And what you see is that as long as the Eddington factor remains below 1, we don't have any inflation at all. We have ordinary stellar models as everybody else. As soon as the Eddington factor hits 1, the things blow up, so to speak. I mean, they're still hydrostatic. They inflate. Okay. Now, is that all dream, or is that reality in real stars? Now, there's a few lines of evidence showing that perhaps inflation really happens in nature. And this is a work from Norberto Castro et al. Norberto is from Tenerife as well. He's currently in Bonn. And so what he has done is he has surveyed 600 stars in our galaxy and put them into the spectroscopic Hertzsprung-Russell diagram. The nice thing here is distance does not matter. Reddening actually doesn't matter either. And so we can just look at one of these figures here. The distribution of the stars is shown here as a grayscale background. And what you see is that there's a few things which otherwise we could discuss, but the main thing I want to point out is that if we look at stars which are roughly above 30, 40 solar masses, we have this extended blob here. Now, that's pretty much phenomenologically what we're predicting. Actually, you see our stellar models here as background in blue. So we're not predicting it exactly the same place. We would expect it a bit earlier, a bit higher up here. But otherwise, these guys here are very hard to explain. They would not naturally come out of stellar models otherwise. And so I think this is one line of evidence showing that perhaps really inflation happens in nature. This is a color magnitude diagram of Westerlund 1. Westerlund 1 is one of the most massive star clusters in our galaxy. And the nice thing is here we can use the color magnitude diagram because distance doesn't matter again, because all stars are at the same distance. And so what you see here is in the lines denote evolutionary tracks from Geneva models which do not include inflation in their models. And what you see in as the colored circles, that's the stars in Westerlund 1. Again, from the distribution towards cooler temperatures, I would think we would not expect so many stars here if inflation wouldn't exist. So it's not clear-cut evidence at all, but I think there is some hints that perhaps inflation can exist. Now there's a few other things which come about with this inflation, and one is the turbulent pressure. So I explained to you that when the Eddington factor gets close to 1, then the envelopes of the stars become convectively unstable. Now, if that's the case, then, well, the opacity is relatively high in the subsurface layers, but it's hard for convection to transport any energy because, so the convective flux is essentially specific heat times density times convective velocity times the temperature difference between the blobs and the surroundings. I explained that the temperature difference goes to 0 if convection isn't efficient. That's why the convective flux goes to 0. Now the way convection tries to compensate is to get even higher convective velocities to try to transport still some energy. And then what happens is that the convective velocities may approach the sound speed. And when that is the case, then turbulent pressure starts playing a role. What is turbulent pressure? Well, gas pressure is the pressure exerted by the gas particles bumping into each other. Turbulent pressure is the same thing. We have the convective eddies which bump into each other and that way exert a pressure into the surrounding. And we can write the convective pressure, the turbulent pressure in this way here. And when we do that and look into our stellar models, for example here in a 60 solar mass model, then we can actually see that in this iron convection zone here, so sorry, this is effective temperature as the star evolves. Actually it evolves this way, from the 0H main sequence becomes cooler. And that's an optical depth scale. So here we are at the surface of the star. Here we have an optical depth of 10, 100, 1,000 and so on. This is the iron convection zone where we have the iron opacity peak. And what we see is that indeed in this subsurface convection zone, the turbulent pressure relative to the total pressure has levels of the order of a few %. Now, this is kind of serious because turbulence is something intermittent. The blobs bounce around, but they are large scale. And so that means locally, the hydrostatic equilibrium is disturbed at the level of a few %. And so we think this has to do then with observable phenomena at the stellar surface, because if this bouncing around happens beneath the surface, waves can travel to the surface. And so what we see here is, for example, line profile variability in a O supergiant star alpha Cam. We just have to look at one of these pictures here. So you see The helium line here is varying substantially. Sergio actually in a nice paper a few years has shown that line profile variability can relate to macroturbulence. So again, this is macroturbulent velocity here, line profile variability here, and well, he found very nice relations saying that these two types of phenomena are related. And what we have done also in collaboration with Sergio in Bonn is we have basically mapped out the Hertzsprung-Russell diagram in a way where we find turbulent pressure to play a role. So here in this color scale you see that turbulent pressure is most important in the most luminous stars, which have most of the problem with the Eddington limit, and still it's sizable here, but then it decays below. Now people here in the Canaries have measured macroturbulence in many galactic stars. So all these dots here are measured stars, and you see it not so well in this diagram, but here, that the measured macroturbulence also shows a very clean relation with the turbulent pressure in the stellar models. So the way we try to understand all these phenomena is that we have stars which are very close to the Eddington limit. The energy has problems coming out of the star. Convection tries its best. It reaches convective velocities of the order of the sound speed, and this gives rise to turbulent pressure, which maybe we can see then at the stellar surface as macroturbulence and also as line profile variability. Again, if we would ignore the Eddington limit, none of this would happen. And so that we see all these things as macroturbulence and line profile variability is in support of these kind of ideas that the Eddington limit really plays a role. So let me just summarize. We have the iron peak being very important in the subsurface layers of massive stars. This makes stars above 30 solar mass to reach and even exceed the Eddington limit. So we get inflation, inflated envelopes, we get turbulent pressure fluctuations. The macroturbulence may be interpreted also as a manifestation of high-order non-radial pulsations. I won't go into details here. And we see line profile variability. Now, we also looked at lower mass stars in connection with the hydrogen opacity peak. And so what you see here is now the spectroscopic Hertzsprung-Russell diagram from very low mass to high mass stars. So far we talked about the guys up here, above 30, 40 solar masses. You see that this red area here is caused by the hydrogen opacity peak, which, as I showed you earlier, is much, much stronger. It can be, the opacity can be up to the 10 to the 5 times the electron scattering opacity. And indeed, also here we find turbulent pressure fractions actually up to 25%. So everything which is red can also be higher than 10%. And so we also asked the question, does that have observable manifestations as well? And indeed, so we looked again for macroturbulence in these objects. And so you see, it seems to be it seems to be very difficult to measure macroturbulence in these stars because many of them are rapid rotators. If they're rapid rotators, it's very tough. Then if they're slow rotators, the slowly rotating intermediate mass main sequence stars are often chemically peculiar, so we don't want to deal with that either. So to find non-peculiar stars which do not rotate rapidly, there are not so many. So we need to find stars where we almost look pole on, obviously. But so these guys have been identified. Most of them are from the literature, partly Luca Fossati has studied them in Bonn. And again, we try to correlate the predicted turbulent pressure with the observed macroturbulence. And this is just the cursor. If you leave that away, you see again the correlation is not 100%, but you know, I do stellar evolution since 30 years. We don't succeed very often to predict something which correlates so nicely with observation. So it looks as if the similar phenomenon occurs in low mass stars. And again, there seems to be a connection to pulsations. So all the stars which you see in this plot here are so-called gamma Doradus pulsators. And again, the gamma Doradus stars seem to be excited, seem to be pulsating in high-order non-radial modes. And so we think that the knocking of the turbulent blobs, in this case, the deviation from hydrostatic equilibrium locally can be up to 20%, so it's really strong. It can have so strong effects that the star excites pulsations, global pulsations, so local eigenmodes are excited. So in a sense, if I knock here at the table hard enough, you hear the table's eigenfrequencies, and so I think a similar phenomenon may occur in this case. And for the gamma Doradus pulsators, also the excitation of the pulsation is still debated, so maybe what I tell you here plays some role in them. Now, I think pulsations may have a connection to the Eddington limit in a more general way. So we have the gamma Doradus pulsators here, and next to them is the classical Kappa mechanism pulsator strip in the Edgman-Russell diagram, the delta Scuti stars, the Cepheids here. And so, again, the opacity, of course, we know is the key phenomenon for allowing the pulsations of these stars. And, well, how does that relate to the Eddington limit? That's my kitchen model of pulsating stars. So if you put a pot of water on a stove, you light the fire, wait until the water boils, you put a lid on top, then what happens is that pressure will develop from the steam which evaporates from the water. It will lift the lid, steam will go out, the lid will fall down. Steam builds up again, and this repeats periodically. So I think that's the Kappa mechanism, and you see the lid is the Eddington limit, yeah? So radiation cannot go out. That's the opacity, the layer of high opacity, which prevents the star from remaining stable. Okay, finally, we are underway to relate all this to the so-called S Doradus variables and luminous blue variables. Eta Carina, for example, you all know, is a big mystery. Now, we're far from understanding all of this, but there are a few phenomena which point into the direction that inflation may be related to all this. And so we have one plot here which gives the mass of the inflated envelope as function of the effective temperature in our stellar models. And what you see, or I hope you can read it, is that for the bulk of stars, so especially for the hot stars, the amount of mass in this inflated envelope is actually very small. 10 to the minus 5 solar masses, 10 to the minus 4 solar masses. But then when we go to real cool temperatures, we can reach inflated envelope masses which exceed 1 solar mass. So I think our record holder has 8 solar masses or so in the inflated envelope. And now you can imagine if you have such an object which has an inflated envelope with 8 solar masses, well, in the inflated envelope the Eddington factor is roughly 1, so that means that the binding energy of this thing is close to 0. And so this is, at least from my point of view, the first time I see that I see stellar models which may allow to eject several solar masses of material at the same time in a natural way. We are not there yet, but we will definitely investigate these models further and see under what conditions we can actually really unbind the envelope. One phenomenon which I didn't mention, which we see consistently actually in almost all our inflated models, is that the envelopes also undergo global pulsations. And so maybe having such a massive envelope pulsate in a global way is one way to, at one point, kick it off. Okay, so that's my story. Let me just summarize the main points. So if one only considers the electron scattering opacity, the Eddington limit is irrelevant for stars. But we have to consider as a full opacity. Even in that case, at the surface of the star, the Eddington limit is never exceeded. So the idea that stars reach, very massive stars reach the Eddington limit at the surface and then have a Eddington driven wind seems not to be a possibility. The Eddington limit is reached below the surface in layers which are sufficiently deep that they can't drive a wind, that one cannot drive a wind there. And this phenomenon leads to inflation of the envelope. And this inflation occurs on a nuclear timescale very slowly. The turbulent pressure can be very high. We see macroturbulenc. In low mass stars, we see similar phenomena, maybe also relating to non-radial pulsations. Perhaps the classical pulsators are one of the manifestations of the Eddington limit. And as a summary, whenever you see stars close to the Eddington limit, there's a high chance that you can see them varying on the human timescale for you to observe and enjoy. That was all I have to say. Thank you very much.
Thank you.
What is the role rotation may play in these models?
Very good question. Rotation will complicate matters enormously because we have an extra force which is directed outwards, a centrifugal force. So I think rotation will actually cause the Eddington limit, the effective Eddington limit, even to come down to even lower masses. And it may cause phenomena which are, well, not spherically symmetric anymore. So one of the types of stars which came to my mind when I thought about this is the B bracket E supergiants. Now that's for the specialists among you. That's stars which seem to have a two-component wind, a fast wind from the poles and a very slow wind from the equator. And so it could be that this leads to a very interesting and partly complicated phenomena.
Okay.
Yeah, I have a very similar question. The way we measure the Eddington, whether a source is sub-Eddington or above Eddington, is by measuring the radiation, but the stars might have other channels to release the energy, and one is rotation, might be magnetic fields, pulsations, jets. Is that I suppose that might play a role to make a source to be sub-Eddington, when we measure sub-Eddington in terms of radiative luminosity?
Well, you're talking about ways to transport radiation.
Yeah.
Well,
energy, because you measure...
to transport energy, my mistake. Rotation will not help you there, I think. Besides convection and radiation, maybe you can transport energy by waves. Yeah, also magnetic waves, alphate waves, and so on.
So you imply that the knowledge is that the major channel for transporting energy in a star is radiation. Is the way.
It would be radiation or convection. I mean, convection is the alternative which stars have. All the other mechanisms I would call exotic, and I would not exclude that they play a role here, but I don't easily see a way to employ them.
Questions? Actually, it's a kind of double question. Could you comment on the role of metallicity and on the spectral variability? Would you expect that from time to time you have a burst that allows you to see the UV, the far UV spectrum, so that the spectrum of the star is going to change a lot in these cycles?
Okay, so that's two questions. Metallicity first. I basically discussed two major opacity peaks, one by iron, one by hydrogen. Obviously, the hydrogen one is not related to metallicity. The iron one is, yes. So the inflation of the massive stars, which I showed you, we expect that goes away if we go to the early universe. And actually, we have model grids at lower metallicity, and that's what we also see in the models. Unfortunately, we didn't find an easy way to test that observationally yet. But the expectation is that the iron peak plays less and less of a role as we go to low metallicity. Now the second question, whether you expect bursts, you say? So
a significant change of the spectrum, for instance. Well, I imagine what you have been describing, like from time to time, the lid that you were mentioning is open, and you're allowed to see the interior of the star. Well, at least the inner layers of the interior, or deeper layers. And so this will come with a extra emission of UV radiation.
I guess in the globally pulsating stars, you would see temperature changes and maybe also changes of the optical depth of certain layers, because opacity does change. In the stellar models which we produce, we don't see much of that, because well, the main phenomenon which causes time variability there is the convection itself, and that is small scale. So from that by itself, you would not expect a global change of the global characteristics of the star. Now, as I said, also we find these models do show actually radial pulsations. We haven't investigated that too much detail yet, but it looks that these pulsations are hard to detect, even though the radius change is appreciable. The luminosity doesn't change very much at all, so we don't expect a large magnitude change in the brightness of the star. But we're working on that still.
Thank you.
If there are no, yes. Yeah, and about the peculiarities, I mean, in the elements, that because as you are approaching to the, the external, let's say, to the surface, and these huge stars, they are evolving so quickly and they're producing the elements. So this process somehow should be reflected in the elemental peculiarities in some stars.
Well, so the outer layers are convective, so we not expect any peculiarities coming up from diffusion processes, like we do see in the intermediate mass stars. And the mass in this inflated part of the star is very small, so that means that we do not expect to see nucleosynthesis products from the core at the surface. Now, of course, that's just from the processes I discussed. These massive stars have other ways to bring material from the core to the surface, for example, rotationally induced mixing or other processes. But that's a different story, so I would not mix these two phenomena. Just from what I said, I would not expect chemical peculiarities.
Okay, there
there are no more questions, so let's thank the speaker again.